So you want to do the reducing agents first? Okay, so the first thing is you got to get the inventory. So Fe2 plus chloride, potassium, iodate, H plus, and chloride again. It was HCl, right? Was the acid? Yeah. But then we have to identify the, you want to do the reducing agents or the oxidizing agents first? All right, iron 2. The reducing agents are on the left side or the right side of this? They're on the right side. So do you see Fe2 plus on the right side? Yes. Right here. Do you see it? Fe2 plus. Oh, I was looking at Fe3 plus. So this is a reducing agent. Chloride. Is it on the right side or the left side or both sides? Fe2 plus is tricky because Fe2 plus is on both sides of the chart. Some people will just see it on one side and then assume it's not on the other, but it's on both because Fe2 plus can go either way. It could be a reducing agent or it could be an oxidizing agent. Is Cl minus on the left side or the right side? Right, so it's a reducing agent. Potassium ion. It's on the left side, so it's an oxidizing agent. Iodate. It's an OA, but we need H+, so we'll link them together. And then H+ alone is an oxidizer. Fe2 plus can go either way, so it's on both sides. So we'll write OA and RA. All the others are just on one side. And so we got to pick the strongest RA. Oh, you know what? I'm missing something. What am I missing? Water, yeah. Water can be an oxidizer or reducer here. Okay. Water occurs on both sides, so it's an RA and an OA. And so which RA is the strongest? Strongest RA is? Oh yeah. Which is going to be what? Fe2 plus is correct. Fe2 plus will be our RA. What will be our OA? Iodate and H+. This will be our OA. And so all I do is I copy the reactions down. If Fe2 plus is our RA, then it's Fe2 plus goes to Fe3 plus an electron. And then our OA here is IO3 minus plus, and just copy it down off the chart. So IO3 minus, I need 2 of those plus 12 H pluses. So I go 2 IO3 minus plus 12 H plus. Plus 10 electrons. Yields I2 solid plus 6 H2O liquid. Okay, then I need to combine these two half reactions. I have to make sure that the electrons produced equal the electrons consumed. And so the top one I'm going to multiply by 10 and add it up. And so I'm going to end up with 10 Fe2 plus 2 IO3 minus plus 12 H plus. The 10 electrons cancel out the 10 electrons. This is going to yield 10 Fe3 plus I2 solid plus 6 H2O liquid. Then I check for driving force. Fe2 plus is our Ra. IO3 minus and H plus is our OA. That's what we determined above. But going backwards, you know, there's a conjugate relationship. So Fe2 plus, the Ra, forms Fe3 plus, the OA. In other words, the oxidizer gains electrons, going backwards. And the OA is going to produce its conjugate Ra. And so I2 solid plus 6H2O must be the Ra. And so we'll label these. This is our Ra, this is our OA. This will be our OA, this will be our Ra. And then we compare. We compare either the two OAs or the two RAs. Let's compare the two OAs. Iron 3 on the right versus iodate and H plus on the left. It looks like iodate and H plus is a stronger oxidizer than iron 3. So iodate and H plus is a stronger oxidizer than iron 3. So we say that this is stronger, this is weaker. If that's the case, then iron 2 plus must be a stronger reducer than iodine. Here's iron 2 plus, which is a stronger reducer than which iodine? It has to be this iodine. So iron 2 plus is a stronger reducer than iodine in water. And so we expect a reaction because we're going from stronger to weaker OA-RA. And so reaction's expected. There. Okay, this is an example of a redox reaction that you would expect to see on the final exam, you know, where you have to inventory it and then look at the chart. Go on from there. Uh-huh.
What equations or formulas for nitrogen plus reaction
What equations or formulas? That's a tough one because there are, you know, formulas that are derived from other formulas.
So you're going to give us the basic.
I'll give you all the basic formulas. If there's one that you're uncertain about, ask me, and I'll.
Is your test all chapters in order?
For the most part, go by order. Okay. What other questions do you guys have? Uh-huh. The written part? Written part is just chemical reactions. Maybe I'll have you sketch an electrolytic cell. Maybe not. No, I'm not going to ask you to sketch it.
Reactions.
Just reactions.
Or 4.
Like 3 or 4 reactions. How many do you want? 3 or 4?
5.
5? 5 might be too many. What's that? Yeah, right. Exactly. Exactly the same thing. I think last semester I gave 4 or 3 or 4. 1 redox, like this. 1 metathesis. 1 acid base. If I did 4, I might have given a skeleton redox. I might not give a skeleton. Skeleton redox is chapter 5 in Chem 1A.
So 3.
Yeah, maybe, well, so a lot of people wanted 4 because that spreads out the points more. So I'll just say 3 or 4. Well, 60 questions. How many chapters do we have?
7.
Well, 25, 24, 20, 19, 18, 17, 16, 15, 14. 9 chapters. 60 divided by 9. How many questions is that? 6 questions? About 6 questions. Okay, about 6 questions per chapter. The final? No. Created the final? Not the final version. Unfortunately, no final practice. Just look at your multiple choice, and then there's going to be calculations on there. So some people are thinking it's just conceptual. No, they're calculations. But again, it has to average about 2 minutes per question. Easier calculations. If I have a calculation that requires 30 minutes, then I have to make some questions very, very short, or quick. No, I mean, what, deriving the rate law? No. But questions about the steady state approximation, yes. You might see. Now, how many? I can ask 6 questions per chapter. So do you think I'd ask how many questions about the steady state? Maybe 5 out of the 6 for chapter 14? No. Maybe 0? Maybe 1?
Are you also the professor who, like, let's say you test us for the final on stuff that didn't show up on the exams?
What do you mean show up?
Like, let's say, for example, in chapter 19, you had to place problem, but then the exam was based.
No, the stuff you're going to see will be stuff that was covered in class, but it might not have been covered on the test.
Any lab questions that would be in the exam?
Any lab questions on the exam? I have in the past put a lab question on the exam. It wouldn't be like, I wouldn't put a question like, what is the color of potassium dichromate? It would be like a question like this, you know. I might ask like a question like, what is the strongest acid out of the group? You know, but that's not necessarily lab. But you know, it's a concept that's covered in lab. Or I might ask, you know, the pH of a buffer solution, something like that. It might be. It might not be. You know, this is related to lab. CV plus OH minus yields CVOH. We did a plot of CV, ln of CV versus time. And this came out linear, right?
Yeah.
For most people, this came out linear. Some people, maybe second order, came out linear. And so we got a linear plot of ln of CV versus time, means it must be first order in terms of CV. Except we had to do something first. What did we have to do or prove first before coming to this conclusion? What did we do to the concentration of hydroxide? Well, so you asked me if lab questions are going to be on there. Here's a lab question that's on there. Help if we could see. Turn off the volume. In this reaction, what did you have to do first before you could determine the order of the CV? You had to make hydroxide very high. In other words, you had to make it pseudo M order. Otherwise, the hydroxide ion concentration would change and screw up potentially your rate. What you see in the graph is the overall order, not the individual order. And so this is the exact same thing, except I didn't use CV and hydroxide, I just used A plus B. A plus B yields AB, or product. If I didn't make hydroxide concentration very high, then both change. If both change, both will have an impact on the rate, which means you don't know. You know, if it's first order overall, is it zero order in CV, i.e. zero order in A and first order in B? If it's zero order in A and first order in B, then the plot's still going to come out linear because A's got to react along with B. And so it's false because if I said we're going to make it pseudo M order, then it would be true. Or if it was just only one reactant, you know, if there's no B here and it was only A goes to product, then it's true. Okay? And so this is a lab question. You know, that was the lab-related multiple choice question. So is there lab? Yes, there's lab. You just saw it just in the exam 14. There's a lab question in there. Although it didn't look like a lab question.
For chapter 14,
Mm-hmm.
at extremely low enzyme concentration, is the order of second? Yes, is that the first one?
It's zero order.
What, zero?
Yeah. At extremely low enzyme concentration, you could keep doubling and doubling the substrate, and nothing's going to happen because you've run out of enzyme. It's not going to go any faster. So it goes zero order. Okay, other questions? Uh-huh. Yeah, we're reviewing tomorrow too. So if you have more questions tomorrow, you can ask them.
Exam 14 of question number 8. For the reaction A plus B with product, a lot of element A with a T is linear. The reaction is blank order for A.
Okay.
Is that the first one, zero or second?
Actually, it's the same question? A different question? Okay. Yeah, basically, you didn't catch it. That works if B, the concentration B is very high. If the concentration B is very high, then the rate only depends on A. If the rate only depends on A, then we can make plots like this. But if the concentration of B is not very high, then the rate, that is the graph of A or the graph of B, is going to depend on the overall order of reaction. And so if a plot of ln of A is linear, it could be that A is zero order and B is first order. And that's going to give you a linear plot. It doesn't necessarily mean that A is first order, because we have two reactants. If you go back, it's very tricky. I try to make the distinction clear. The distinction is the integrated rate laws and the graphical analysis only works in decomposition. Single reactant goes to product type reactions. Okay? All right, other questions?
Wait, what's the answer for 8 unknown? Oh, no.
The way you want to study for this is, you know, if there are only 6 questions per chapter, then you want to think, what are the most important calculations? What are the most important concepts? You know, and then you try to guess. When I was a student, I always tried to guess the questions that were going to be on the test. And the way I guessed was by, you know, thinking what was the most important thing the professor talked about, or what did they spend the most time talking about, that kind of stuff. Okay, let me get you and then you.
In chapter 24, you know how we did 2 parts. The first part was like relating and like drawing quickly. Awesome stuff. Are we gonna tune in these?
Yeah. Some people turned them in today. I can give it back to you. You take it with you on the day of the final. I'm just going to look for certain observations or something. As long as it doesn't have to be perfect. It doesn't have to be complete as in 100%. It should be like 80 or 90, 80 to 100% complete. And so you don't really have to, you don't have to clean it up. You know, I expect lab notebooks to be messy. So don't worry. But, you know, you should have like things like a table of contents in there. Did I give you that handout? No? There's no handout?
You just told us to make one in the beginning of
All right.
the semester.
Number the pages. Make a table of contents so if I'm looking for a particular lab, I can see if you have it or not. And that's it. Dates are good, but you don't have to date every page. You should just date the lab observations. That's it. Okay, Joy, did you have a question? 13, number 5? 14, number 5? All right, what does number 5 say?
Radioactive 137 has a half-life of 30 years. Something about ingesting it, and then the biological half-life is about 70 days. Sequestering shares will get the complex, or I can't by complexes, but it's FE4 and then brackets. FE and then cyano complex. Ligands, 6 ligands. Cyanide and then what is the half-life of 30 days and how long will it take to reach 99%? Bio 137. And the answer was 199 days. But I don't know why. I guess I got it right.
Well, radioactive decay, this is first order. And so what we do is we look at the integrated rate law. And so this is the concentration time T, this is initial. How much reaction? 90% reaction? 99% reaction. And so that means I've lost 99% of my original. So how much do I have left over? I only have 1% left over, right? And so that's 0.01 times the original, divided by the original. And so at time t, I only have 1% of my original left over. And so the original cancels out, and it's just ln of 0.01. This is equal to minus k. K is 0.693 over t1 half. T1 half was 70 days, was it?
Yes, 70 days. But then it gets rid of the base time, I mean, half-life, it's 30 and 70. Yeah, when it forms the complex ion, it reduces to 30 days. So which days will you use? 70 or 30?
Oh, if you use a complex to get rid of it faster, then we use 30 days. And then solve for t. Okay, other questions?
For 15, I think it's full credit. I really want to know why.
What was 15?
It was proposed a two-step mechanism in determining the ring law, class reversible, slow for the 2NO plus O2 equals 2NO2. Yeah, absolutely.
Tell me what your first step was.
I did 2NO plus O2 equals 2NO2. And the second step was NO3. I mean NO3.
Okay, let's redo it then. What was your first step?
It's NO plus O2 equals to NO3. And then NO3 plus
Okay, let's stop here for a second. NO3. Let's draw out the Lewis structure for NO3. I know NO3 minus. Well, what would NO3 look like? Oxygen is 6, nitrogen is 5, so 3 times 6 is 18, plus 5 is 23 electrons. That'll be 23 electrons. Nitrogen doesn't have an octet, so we'll make a double bond here. How does that look? It doesn't look very stable, does it? It doesn't look very stable because, one, you have a negative charge on this oxygen and a, well, actually 1, 2, 3, 4, 5, 6, and a positive charge on this nitrogen. Maybe that's okay. Well, you also have a free radical. Free radical is this dangling bond here, this lone electron. And so not only do you have this formal charge, but you also have a free radical, which isn't so stable. And so making this might be difficult. Versus this. If I had an NO collide with an NO, I could form N2O2. N2O2 is 2 nitrogens is 10, 2 oxygens is 12, so 10 and 12 is 22 electrons. And so this is 8, 16, 18, 20, 22 electrons. And then these nitrogens don't have an octet, so we'll make an octet. There. And so N2O2 has 0 formal charges and no free radicals. And so which one would be more likely product here? N2O2, which is a lot more stable than NO3. And so NO3 is not good when we have a choice between NO3 and N2O2. Would have gone with N2O2. It's a lot more stable. Okay, other questions?
Oh, yeah.
So how do you find the special text?
I know what you did. The problem is the rate law that you get should match the experimental rate law. Did the rate law that you got match the experimental rate law?
The first time, yes. Because I took all of them 2 times. And then,
If you don't know, I mean, which one to go with, you should just pick one. Because if you give me a choice, I'll pick the wrong answer. And so some people, they'll, not saying you do that, but some people might hedge their bets and then try to make sure they have both answers. They aren't sure which one to go with.
I have a rate law, but then I realized that it has to be related, so I did my math and then substituted and I got the rate law.
Okay, is that rate law, does it match the experimental rate law? A mechanism should do 2 things. A mechanism, the net, when you add up the steps, the net reaction should match. And when you figure out the rate law should match experimental.
So is the rate law the net one the experimental one?
No, I need the rate law, does it match the given rate law? I mean, well, let me just make it a long story short. You know, you did it right, but you did it using the steady state approximation. With a steady state approximation, the rate law is not going to match unless at the end you say, let's assume that. You have to say, we got to assume that it's like a balloon and it's a slow leak out of the balloon. And so that K2 is extremely small. If K2 is extremely small, then the rate law that you get from the steady state will match the rate law that you get from fast reversible. And so that was the only problem.
I know why I tried, because in your practice exam, you mentioned steady state approximation and then we tested it and
Yeah. Yeah. That makes it especially tricky because it looks the same, but it's not the same. I've thought about that. You know, I've thought about, maybe I should make it totally different. It might be less tricky that way than having it look kind of the same. So sometimes I italicize it or I make it in bold. But if you did one more step, you know, with yours, then you would have had it. And the one more step would have been to make an assumption. Okay, any other questions? Number 1 on 14, what was the question?
VR2 is produced as 3 per second. VR6
VR2 is produced from what? So if we, let's say we consume 3 moles of bromine. If we consume 3 moles of bromine, or not consume, if we produce 3 moles of bromine, how many moles of bromide must have reacted? 5. And so for every 3 moles of bromine that are produced, 5 moles of bromide react. And so if we have 3 times 10 to the minus 5 moles of bromine, then we must have consumed 5 times 10 to the minus 5 moles. Because it's a 3 to 5 ratio. Mole ratio. Okay. Oh, you know what? I have your report. Actually, let me. Yours and yeah, formal reports.
Did we get it back already or?
No, well, let me give it back to you officially.
Oh, like the grades?
Yeah, here.
What is it out of?
The formal report's out of 30 points, and I didn't take that much off, I think. Joy, Ultima, and Claudia,
Thank you.
Angel, okay, Sergio, Winston, Ashal, Emily. I was looking for, did you talk about all the reactions that were taking place? The redox, the acid base, and the metathesis or precipitation, and kind of how they operated. Jose, that is, dichromate is a strong oxidizer because this. Oscar? Eric? And Nicole? Haruka?